Let me record this, and now it's recording. Excellent. So I just want to point out that there's a new homework assignment came out. It's due Sunday, I suppose, or Monday, one of the days. It's probably going to cover like a system with repeated eigenvalues or complex eigenvalues, which we're going to talk about some of it today and then some of it on Thursday. And obviously, they're going to be covered in lectures as well. So the first thing I want to begin with today is I wanted to kind of recap what we talked about last time. So recap. We talked about a system of linear ODE with distinct eigenvalues. So if we had a system that looks like an xy derivative equals some matrix A, coefficient matrix, times xy, and then we just focus on A to find the eigenvalue. So A will give us eigenvalues. They're different, lambda 1, lambda 2, they're not the same. And then we can, if we have two different real eigenvalues, we can always find two eigenvectors corresponding to them. So, and corresponding eigenvectors, V1 and the V2. They're linearly independent. Which means that if you take V1, you multiply with some number, you're never going to get to V2. That means they're linearly independent. It means that one doesn't come from the other one. One is not a scalar multiple of the other one. So in this case, the solution has the form x of t, y of t is equal to c1 v1 e to the lambda 1t plus c2 v2 e to the lambda 2t. So that's just the form of the solution. So if we know those eigenvalues and those eigenvectors, then we can just take them, put it into this form, and then we get a solution to the system. That's what we talked about last time. And today we're going to lay down, in a few minutes, we're going to look at cases where we have only one eigenvalue that's instead of two different ones, we only have one that repeats. And then we're going to look at how the solution might change. But before I do that, I wanted to spend a little bit time on face portrait. Face portrait with system have distinct eigenvalues. With distinct real, I should emphasize the real, eigenvalues. Because if we have complex eigenvalues, they're also distinct. But now we just talk about real ones. That's the example that we talked about last time. Let me write down the example. The example we had last time, recall, example was x prime equals negative 5x plus y, y prime equals 4x minus 2y. So when we solved this system last time, we end up with lambda 1 equals negative 1, lambda 2 equals negative 6, and then we end up with a v1 is equal to 1/4. V2 corresponding to lambda 2 is going to be negative 1, 1. That's what we had, and then we were able to write down the solution. Let me just write down it quickly. So that solution was x of t, y of t. If we just follow the formula I wrote above, it's going to have this form, right? C1, V1, e to the lambda 1t, and then C2, V2, e to the lambda 2t. So that's going to be C1, V1 is 1, 4, e to the lambda 1, which is negative 1, so negative t, plus C2, V2 is negative 1, 1, and then e to the lambda 2, negative 6t. So that's the solution. And we have done all the work last time. So today I want to begin by graphing the phase portrait of this. Solution. So to plot it, for me, I always plot the vectors first. And then I'm going to use the eigenvalue to tell me the direction along those vectors. For example, I'm going to plot 1, 4 first. So if I plot V1, 1, 4, so that's x equals 1, y equals 4, 1, 2, 3, 4. 1, 4 give me this vector, V1. Normally when we plot a vector, we draw an arrow at the end, right? That's how we plot a vector. But in this case, we actually don't put the arrow at the end because the vector, for the phase portrait, the direction not necessarily away from the origin along the vector. So we don't draw the arrow, just draw the vector without the arrow there. And then the arrow will be from the eigenvalue. So lambda 1 will tell us the direction. So since lambda 1 equals negative 1, which is less than 0, so the direction along V1 is going to be pointing towards the origin. Because lambda is negative 1. Sorry, not negative 1. Negative 1 less than 0. So because it's less than 0, so it's going to point in towards the origin. And then we're just going to take this vector V1 and we're going to reflect it over the origin by rotating that 180 degrees. So this is the reflection of V1. And then we're going to reflect the arrow as well, so that's going to point towards the origin in the third quadrant. So that's the first vector. And now we move on to the second vector, V2, and then we're going to do the same thing. We're going to plot it, and then we're going to draw the arrow on that vector using lambda 2. So V2 is negative 1, 1, so negative 1, 1. So that's going to give me this vector. And then lambda 2, so since lambda 2 is equal to negative 6, again, that's less than 0. If it's less than 0, it's always going to point towards the origin. If it's positive, it's going to point away from the origin. So this is going to be towards origin again. And now we're going to reflect this. Again, draw an arrow pointing towards the origin. So those four vectors, the V1, V2, and also the reflection, it's going to tell us how the solution will behave. For example, if we have a solution, let's say it's starting here, near this, a little bit below this second vector V2, because it's so close to V2, the solution is going to follow that vector, move along that V2, and then go towards the origin like the vector does. If it's over here, it depends, it might move up, but if it moves up, it's going to follow V2, or if it's going to move down, it's going to follow this vector going towards the origin. So it really doesn't matter where the starting point is, it's always going to move towards the origin eventually. So even if it's here, it's going to move towards the origin, whether it's going to go directly or whether it's going to go up a little bit, move towards the origin, or maybe go down and then move towards the origin, depends. But nevertheless, it's just going to go towards the origin. So it doesn't matter where the solution begins with, it's going to move towards the origin. This phase portrait, we sometimes call that a sink, because the solutions are sinking towards the center there. It's also called a stable node. And this thing happens when we have lambda 1 is negative, lambda 2 is also negative. Both eigenvalues are negative. We always end up with a sink, always a stable node. Questions? Now, a separate example we didn't work on, but I'm just write down the example, and I'm going to just write down the eigenvalues and the vectors from there, which is x prime equals x plus 2y, y prime equals 3x plus 2y. And if we were to solve this fully, we get lambda 1 equals negative 1, lambda 2 equals positive 4, v1 is going to be negative 1, 1, v2 is going to be 2, 3. And I'm not going to write down the solution because at this point, if we want to write down the solution, we could just put into the formula. But let's look at the face portrait of the solution. So I'm going to plot V1. So that's going to be negative 1, 1. It's going to be this vector. And because lambda 1 is less than 1, so it's going to lambda 1 is less than 0, so it's going to point towards the origin, and the reflection is also going to point towards the origin. And if I plot V2, 2, 3, so 1, 2, 1, 2, 3, so I get this vector. This vector V2 corresponding to lambda 2, which is 4, so that's positive. When it's positive eigenvalue, it's going to move away from the origin. So the arrow is going to point away from the origin. And when I plot the reflection, again, the arrow will be pointing away from the origin. So if we look at this one, it depends on the starting point. If we start with a point near V2 at this part, we're just going to move along the vector, move away from the origin. But if let's say we start with a point here as the initial point, and it's going to follow along this vector, the reflection of V1. So it's going to move along this, looks like it's going towards the origin, but as it gets close to the origin, eventually get really close to V2, then it's going to move away from it. So it's never really going into the origin, because at some point, it's going to move away from the origin. If we start it here, as it moves towards the origin, eventually will move away. So we get this solution curve. If we, starting here, we move towards the origin, but then we have to move away from it as we get close to V2. Same thing here. And if we, in the top part, that's going to move towards the origin and then move away. If we have the lower quarter, we're going to do the same thing. So that's what the solution curve looks like. And the origin in this case is, well, this portrait is what we call a saddle node. It looks like a saddle because part of it is kind of, oh my gosh, this is not how you describe this. So you kind of have this cross section, 2/4 of it is like going downwards, the other two is going upwards, basically. And a saddle happens when we have one lambda, let's just say lambda 1, doesn't matter. One lambda is going to be greater than 0. The other one is going to be less than 0. One positive, one negative. So that will give us a saddle node. And the next one, I don't have a system of equation. I'm going to make up some lambda. Let's see, lambda 1 equals 1, lambda 2 equals 4, And let's see, eigenvector v1 is 1, 2. Eigenvector v2 is equal to 5, negative 1. Doesn't matter, just making up some example here. And if we plot the phase portrait, so vector v1, 1, 2, that has a positive eigenvalue, so it's going to point away from the origin. The reflection also going to have an arrow pointing away from the origin. Vector v2 is 5, negative 1. 1, 2, 3, 4, 5, negative 1. And that also has a positive eigenvalue. So that's going to, again, point away from the origin. The reflection also going to point away from the origin. So it doesn't matter where we begin with. If we are beginning here, then it's either going to follow this vector on the left or follow this vector on the right, or this in the middle is going to point away from the origin. Now, where does it come from? Well, it comes from the origin. So maybe it's like somewhere near the origin, a little bit far away, and it's going to follow this vector or follow this one. So the origin is kind of acting like a source, the starting point. So this case is what we call a source. And it's always going to be an unstable node. Because anywhere near the origin, it's always going to move away from the origin following one of the directions. So the source is never stable, it's always unstable. The sink, on the other hand, is always a stable node. So a source happens when we have lambda 1 is positive and the lambda 2 is also positive, when both eigenvalues are positive. Questions? No? Okay. Well, in that case, I'm going to move on to the next part. Maybe we can finish early. So I have two examples with repeated eigenvalues. To solve them, well, it depends on how many eigenvectors we can obtain from them. But the process to solve them is the same thing we do. So we just begin with finding the eigenvalue, then finding eigenvector or vectors, and then write down the solution from there. So the first example I have is x prime equals negative 4x, y prime equals negative 4y. So I'm going to convert into matrix equation. X, y prime equals negative 4 is a coefficient of x, but there's no y there, so I'm going to put a 0. And there's no x in the second equation, so I'm going to put 0 there, and then negative 4y. It's negative 4. So those are the coefficients. And then this is the coefficient A matrix. So the first step, find eigenvalues. So lambda or lambdas, depends on how many we have. We need to find A minus lambda I. So that's going to be the shortcut to find A minus lambda I. It's just going to subtract lambda from all the diagonal entries. So that's going to be negative 4 minus lambda, 0, 0, negative 4 minus lambda again. Right, so that's going to that's the A minus lambda I. And then we can find the determinant of this. Just going to multiply the diagonal entries together, right, because 0 everywhere. So we just have negative 4 minus lambda, negative 4 minus lambda, and then minus 0. We don't even have to write it if we set equal to 0 there. well, we don't have to do it now, we can do it later. So now we can factor up a negative 1 from each parentheses. So we get negative 4 plus lambda times negative 4 plus lambda. So we get 4 plus lambda squared. And if we set it equal to 0, we get lambda equals negative 4. Fairly straightforward there. We just have one, right? We don't have two different eigenvalues, we only have one repeated eigenvalue. That's fine. Does it mean that we cannot find two eigenvectors? We might be able to find two. Let's see. So step 2, we're going to find eigenvectors V by using, just like we always did in the past, A minus lambda I times V equals 0. So let's find A minus lambda I first. So take negative 4, put in there, so we get negative 4 minus negative 4, be careful there, 0, 0, and then we have negative 4 minus negative 4 again. So it turns out that this is just going to be a 0 matrix. There's 0 everywhere. Right? Okay, fine, and then we can still use it to find V. So if I take this matrix and then multiply by V, V is a non-zero, so 0, 0, 0, 0 times xy equals 0. And then you can convert it to a system of equations if you like, which is just 0x plus 0y equals 0. Just 0 equals 0 for both of them. There's nothing interesting out of there, right? Just 0 on one side, 0 on the other side. So how is that going to help us finding x and y? In this case, we just have to pick. We don't have any other choices other than just choose randomly. So we can choose the x value. Let's see x equals 1. That still doesn't tell us what y is, right? We could pick y to be 1. That's fine. But usually, this is kind of like a trick, a small trick. So usually, if we have the freedom to choose both x and y, we just pick one to be 1, the other one we pick it to be 0. Instead of have 1, 1, we just have 1, 0. So choose y to be 0. So therefore, we have a vector v1 is going to be 1, 0. Probably the simplest vector we want it to be. Okay, so that's choosing x equals 1. But then you probably think, okay, can we choose y to be 1? And x to be 0. Yes, we can do that. We can also choose x to be 0, y equals 1, and then that will give us a different vector. Let's call it v2, 0, 1. And it turns out that those two are the simplest linearly independent vectors we could have for two-dimensional systems. But linearly independent because it doesn't matter what you multiply v1 with, like any real number, you're never going to end up with v2, or the other way, vice versa. So those two are linearly independent. And both are corresponding to the eigenvalue negative 4. So this is the case we have one repeated lambda, but two linearly independent eigenvectors, v1 and v2, which is a good thing. And the solution we write down is just going to treat it as if we have two different eigenvalues. So the solution to the system at the end is going to be x of t, y of t is equal to c1, v1, 1, 0, and the e to the lambda 1, but we just have one lambda, we're just going to use it, negative 4t, plus c2, v2, 0, 1, e to the lambda 2, but it's the same as lambda 1, so negative 4t. So this will be the solution in vector form. Questions? So nothing different there, really just following what we have done in the past. And it turns out that you can, if you break this down into scalar form, we get x of t, which will be just c1 e to the negative 4t. And the y of t is just going to be c1 times 0, so that's not there, so we get c2 e to the negative 4t. So we get, this is what we call the decoupled solution. Because the derivative of x doesn't depend on y, the derivative of y does not depend on x. So this, you can basically treat them as separate systems instead of a system of two ODEs. Sorry, decoupled solution. So that's that example. And I have a second example, which has, let's see, x prime equals 7x plus y, sorry, 7x plus y, and the y prime is equal to negative 4x plus 3y. And then we're going to solve this just like we normally do by converting this into a matrix equation. So that's xy prime equals 7, 1, negative 4, 3, xy, and we're only going to focus on this A matrix here. And if we find eigenvalues of A, so I'm going to do it a little bit quick here, hopefully we are okay. So A minus lambda I, that's going to equal to 7 minus lambda, 3 minus lambda, 1, negative 4. And the determinant of this is going to be 7 minus lambda times 3 minus lambda minus 1 times negative 4. And it turns out that this is going to be 10 minus 3 lambda minus 7 lambda plus lambda squared plus 4. Oh, sorry, not 10, 21. I don't know why I keep writing 10 there. So 3 times 7 is 21. So we get lambda squared minus 10 lambda plus 25. That's going to be lambda minus 5 squared in the factor form. And if we set it equal to 0, and then we get lambda equals 5. Again, this is just like before. This is a repeated eigenvalue problem. Okay, maybe we can find two different eigenvectors. I don't know, right? But let's, assuming we can find two eigenvectors, let's just use the eigenvalue to find them. So find eigenvector, maybe eigenvectors. So we need A minus lambda I, 1 lambda equals 5. We're going to put it in there, so we got 7 minus 5, 1, negative 4, 3 minus 5. So we get 2, 1, negative 4, negative 2. And obviously we're going to use the same formula we did. So using A minus lambda I times V equals 0, right? So that will be 2, 1, negative 4, negative 2 times xy equals 0. And if we convert to a system of equations, we get 2x plus y equals 0, negative 4x plus minus 2y equals 0. So that's the same thing we have done before. And then from here, we try to solve for x, solve for y. But it turns out that we really, instead of two equations, the second one is a scale multiplication of the first one. So we just have one equation. I'm going to write as y equals negative 2x. But that's two variables, x and y, we don't know, which is fine. We just have to pick the simplest we want, right? So in this case, we can choose a value, perhaps for x. Let's see equals 1, the simplest. The reason we don't pick a 0 here, you know already, right? Because if we pick x equals 0, y will be 0, then v will be 0, 0. That's what we don't, that's a vector we don't want. We want a non-zero vector. So we choose x equals 1. And we can solve for y. So the y will become -2. So that gives me a vector v, which is 1, -2. And then you probably think, like, can we get a second vector out of this by choosing a different value? If we pick let's say we pick x equals 3, then the y will be -6. So 3 -6 will be multiples of this one, so that's not independent from v. Well, you probably think, can we pick a value for y first and then solve for x? It's the same. It doesn't matter what we pick for x and y from here. It's always going to be a multiple of this vector. So it's not linearly independent. So it turns out that we can only get one vector. From this eigenvalue 5. Okay, so what do we do next? So if we only have one vector, there's something important we have to do. So we need to find another vector. Let's call that u, using a minus lambda I times u vector equals v. So instead of having a minus lambda I times v equals 0, or a minus lambda I times u equals 0, we say equals v, the eigenvector we already found. So if I write it down, so the a minus lambda I, we already know that matrix from earlier, which is this matrix after I plug in 5 for lambda. So I'm going to write that down, so that's going to be 2, 1, -4, -2. And then this u vector, I don't know what it is, but I'm going to call it x, y. If you don't like that notation, you can call it a and b. It doesn't matter, it just means that we need to find this vector u. And that's going to equal to this v vector 1, -2. And then we have to solve for x, y like we did before. And then convert it into system of equations, so that's going to be 2x plus y equals 1, -4x minus 2y equals -2. Again, if we look at it carefully, the second equation is the first equation multiplied by -2, so we don't have to write down two equations, just one. 2x plus y equals 1, or you can write it as y equals -2x plus 1. So here again we have one equation, two variables. It's slightly different from the equation we had above, right? Earlier we had y equals -2x, that's it, nothing else, but now we have -2x plus 1. So this is something that you can actually use to check your work. Let's say you solve something like this. You get one eigenvalue, you only get one eigenvector, and then you try to solve for the second vector, and then you end up with the same equation like you did earlier. That means something is not right. Because if you get the same equation, that means you're going to end up with the same vector. You shouldn't have the same vector. So from here, we can choose value for x and y. We just pick the simplest x value. In this case, you probably want to pick, well, 1 is simple, right? But 0 is actually a better one, so choose x equals 0. If we choose x equals 0, the y value is not going to be 0, it's going to be 1. That's perfect. So y will equal to 1. And there we have a vector u, which is 0, 1. Questions? So now we can actually, we have the eigenvector v, then we found this vector u. We can use them to write down the solution. So solution to system with repeated lambda and only one eigenvector corresponding to lambda. In that case, the solution will be x of t, y of t is equal to c1 v e to the lambda t, kind of like a c1 v1 e to the lambda 1t, but we don't need the subscription 1, plus c2 times, instead of v2, it's going to be v times t plus u, and then e to the lambda t. So this is a part that make it different. That's why we need the u vector in the middle. So going back to the problem we had lambda equals 5, 5, and then we have v is 1, negative 2, then we also have u is 0, 1. We can put all of them in here. So the problem we had, so return to the problem. The solution is going to be x of t, y of t in vector form will be c1 v, 1, negative 2, e to the lambda, which is 5t, plus c2, parentheses, v again, 1, negative 2, times t, plus u, which is 0, 1, close the parentheses, e to the 5t. So this is a vector form of the solution. And obviously we can always write down the scalar form, which is read it from the equation, the vector form. The top line will be the x of t. So that's going to be c1 times 1, you don't have to write down the 1 there, and then times the e to the 5t, so c1 e to the 5t, plus c2 times 1 times t plus 0. You don't have to write down plus a 0 there, just c2 times t, e to the 5t. So that's the x of t. And then we can write down y of t in a similar way, which is going to be c1 times negative 2. So I'm going to move the negative 2 in front. So negative 2 c1 e to the 5t plus c2 times negative 2t plus 1. You can move that in front of c2, but it doesn't matter where it goes. And then e to the 5t. Questions? It's really similar to what we have done before, but the process of finding the u vector is sort of like the new process. And also the solution at the end has this u, obviously v times t plus u, so that's the other way we usually forget to put in the correct form. Does that kind of make sense? So that's really the only new thing with this repeated eigenvalues. Obviously, the phase portrait will be different. If we have time next time, we will cover that. But for now, we just don't. Shall we finish early today? Why not? Yeah. Okay.